I just want to give you some notes for those people that are absent. If you remember on Friday, we did a little Google Classroom activity. So I'm going to jam over there. Let's take a look at that guy. Do you remember how we were looking at this little video at the very beginning? They start with one circle, and on stage one, it breaks into two circles and then keeps breaking apart, right? So, what was going on there? In stage one, we had two circles. Let me get back over to my pen tool. We had two circles. And on stage two, we had four circles, and then it broke into eight circles. And maybe it stopped at 16, right? So if we were going to come down here and try to write a formula for it, let's say we were on stage X. Well, it was 2 to the first, 2 to the second, right? This is 2 to the second power. 8 is 2 to the third power. 16 is 2 to the fourth power. Every time it was doubling, right? The number of circles. So this would be 2 to the x. This is called an exponential function, right? So 2 to the fifth power gives me 32. So if my question is like, when are there 10,000 circles? Excuse me. How many circles are on stage 11? I skipped this one right here. All you got to do is stick 11 into this function right here, right? So like if I want stage 11, I would just do 2 to the 11th power, and that would give me some big number. I'm cranking on my calculator here real quick. 2048. So 2048 circles, right? So you would just take 2 to the 11th power, and that gives you 2048. But what if the question is, when will there be 10,000 circles? So in that case, we're given this side of the table, right? We want to know 10,000 circles, and that might not be on an exact stage. It might be between a couple stages. Now, I realize that might not make complete sense, because we're saying like at stage 4, there's a whole number of circles here, like there isn't a partial circle. So you can't be at a stage like 4.1 or stage 4.5. It was either stage 4 or it was stage 3, right? Now notice, like as they're splitting, maybe somebody could say like at stage 3.5, there's kind of like a partial circle there. So maybe you could consider it as being a continuous function, but somebody would say it's probably discrete. That you have stage 3, you have stage 4, you don't have a stage 3.5. I hope I'm making that clear. But anyways, let's say we could answer the question, when will there be 10,000 circles? 10,000 is definitely on this side of the table. So now we need to know what the x is. So what we're really saying is, 2 to some power, 2 to what power is equal to 10,000. So how do we figure out that exponent right there? Let me just write it right out here to the side. Like 2 to the a is equal to 10,000. How do you get the a out of the exponent? It requires an inverse function. It's like when my integrated 2 students are dealing with like, let's say x squared equals 25, part of the Pythagorean theorem. And I'm like, well, how do you undo a squared function? And they hesitate. They're not sure. Well, the inverse of squared is the square root function, right? So if I take the square root of x squared, I just get plain x. And if I take the square root of 25, right, I get 5. And so that's how we solve for a function that involves squared, right, is you need the inverse function. So this square root function is my inverse function, kind of. Now we're gonna develop more understanding on what it takes to be an inverse, and it's a little bit more complicated than what I just made it out to be. But that's the main idea. So let's take our situation now. We don't have a quadratic. This is called a quadratic, right? We have a exponential function. So on an exponential function, how do you take the inverse of it, right? We've got 2 to the x. We don't have x to the 2 power. We got 2 to the x power. X is up in the exponent. And we want to know, when's that equal to 10,000, right? So what is the inverse of this function? We need an inverse, right? So we can undo and just get plain x. That's what an inverse function would do. It would undo the 2 to the x. So we don't know right now what the inverse function is. Maybe some of you do. But see how that's my goal. When you do the inverse of the quadratic of the squared, you just get a plain x, right? So we want something in here that will do that for us. All right. So the author feels like this is the perfect time to talk about composite functions, because when you take the square root of x squared, so let's talk about two functions here. Let's say we had the f of x function is equal to the square root of x function, and the g of x function is the x squared function. If we do f of g of x, okay, so that means f of x squared. That means I take the square root of x squared. I just get plain old x. So this is showing me that the square root is the inverse of the x squared function. Like I said, there's a little bit more to it than that. But if we can just get x all by itself, we're undoing one function, okay? So this is one place that we see composite functions with inverses, okay? It's not the only place we see composite functions, though. Let me give you a real simple composite function. Like if you had the sine function, you remember the sine function from integrated to the sine's the opposite over the hypotenuse, right? And then you square it. We really have two functions. We have let's call it an f function, sine, and let's say you have a g function, x squared, okay? So this is another example of a composite function, because if I do g of f of x, okay, that means that I'm going to do g of, and then I replace the f of x. I replace what's inside the parentheses with what the function is, sine of x. And then the g function says square anything that's inside the parentheses, right? So now I'm going to write the sine of x squared. So this is a composite function. Let me zoom in on it, because there's a function inside another function, okay? Let's come up with another real simple composite function, and we'll put it over here in our in kind of like our summary, okay? Let's say you had the square root of cosine of x, okay? So the cosine of x is underneath the square root function. In other words, it's inside the square root function. This is an example of a composite function, because we have two functions, one inside the other function, all right? Let's compare that to something that's not a composite function. Let's say you had like x squared plus the cosine of x. See, we have an x squared function over here, and then we're going to add a cosine function. They're separated by addition. We're not doing the cosine of x squared. It's not like the cosine's inside the squared function. Here's the squared function. Here's the cosine function. They're being added together. So I would not consider this a composite function. This is the addition of two functions. This is like f of x plus g of x. Okay, we're doing f inside the g function, something like that, right? Now the notation that we're going to use for that, if we said, okay, so let's say we let f of x equal the square root of x function and g of x equal the cosine function, okay? The notation that we could use to show this right over here would be f of g of x, because the cosine function is inside the square root function, right? Now, the author sometimes uses, and quite often in this section, he uses this notation, f following g, and they'll put that in parentheses, of x. So what I need you to put down is this little symbol right here means following, okay? Now, let's say we went down to the cafeteria for lunch, and we get in the lunch line, and I am following you, okay? So let me put that down. I'm following you, okay? The way we'd write that in math is I follow, and then maybe you. I don't know if this makes sense or not, okay? So this means that you're coming first in line, then I'm next, right? And so up here, when we say f following g, the g function's happening first, and then the f function's happening. So, if you broke that down, we'd be saying f of, and then we'd put down the cosine function because the g function's coming first, and you do whatever's inside the parentheses first, right? And then we're going to take and do the f function to it. So that's a square root function. So I'm going to put the square root over the cosine of x. Let's compare that to this. G following f of x, okay? So that means I'm going to do g of f of x. This is the way we read it when you have parentheses. When you have a circle, you read it like this, g following f of x. Maybe you can put that over here in your notes, right? The circle means following. And when you see parentheses, you read it as of, right? So like g of f of x. And so I'm going to go the f of x function on the inside. So what was the f of x function again? Square root of x, right? And then I'm going to do the g function to the square root function. Well, what's the g function again? It's the cosine. So I'm going to have the cosine of the square root of x. Do you see how the square root of x is inside the cosine function? All right, so this is the inside function right here, inside function. And this is the outside function. All right, you have to deal with the inside function first, then you would do the outside function. This is called composite notation. Let's look at a couple homework problems and see if we can figure this out. So, sometimes when we have algebra, and I show you an example of algebra, and then we have something that doesn't involve algebra, we think, oh my gosh, this looks totally different. Well, let's just try to rewrite this statement right here without the little following symbol. If I go f of g of 1, okay, so I got to look over here at my table. Here's the x value of 1, and then I'm going to go and find the g value when x is 1. So the g of 1 is 0, so I get f of 0 because at 1 the g function is equal to 0. And now what does this notation mean? It means I go and I find when x is 0, and then I do the f function to that. So I'm going to go to 5. So my final answer is 5 on part A. Let's do another one. I'm going to skip down here to this one right here on D. So I personally don't like the little following symbol. It doesn't make as much sense to me as the function notation. And so, oh, wait, I don't have an X in there. I've got oh boy, this eraser is going to be big here. I've got a number in there. So my number is 3. So I'm going to do the f of 3 function first. So that means I go find, let me erase this here real quick because this is a different problem, right? So I'm going to go to where x is 3. That's what that means right there. X is 3. And then I'm going to go to the f function. So that's -1. Okay, so let me put down, I've just evaluated this guy to be -1. So I got g of -1. Now I go to where x is -1, and I'm going to do the g function, and I end up with 0. So this guy comes out to be 0. All right, I hope I'm making that clear what you do with when, if you're given a table, how do you use the table to answer these questions? Let's go to a graph. It's just like the table. It's just that you've got to go find the information from the graph instead of the table. So I'm going to write part A as g of f of 1. And let's go find x value of 1. Here it is right here on the graph, right? And then I got to go to the f function. The f function is this V shape right here because they tell us there's the f function, right? So I got to go down here, and this point right here it kind of got cut off. It's 1, -1, right? That's important because my inside function right here is equal to -1. Now I'm going to do the g function to that. So that means I got to go over here to -1 because I want g of -1. So here's where -1 is on the x-axis. Remember, what's inside the parentheses here, the innermost parentheses is an x value, right? And so we're going to go up to the g function. Here's the g function up here. See how they have it labeled? So my final answer comes out to be 3 on this one because the y value right there is 3, right? This means what's the y value when the x value is -1 on the g function? What's the y value on the f function when x is 1, right? So that's why we had to look over here at 1 and go down to the function. Let's try another one real quick. Let's do this one right here. So I'm going to write it as f of g of 2. Okay. What's the g function when x is 2? So I got to go over here to 2, and then I go up to the g function. Here's the g function right here, right? Oh, look at that. I get 2. So this could be a little confusing because we get the same y value for that particular x value, right? This is the y value down here. This is the x value up here. So now I'm going to do f of 2. Okay. Now, when I say f of, this is now my x value that I'm worried about for my f function. So I got to go to 2. Okay. And then I'm going to go down. Well, I was already at 2, wasn't I? I'm going to go down to the f function down here, and I get, oh my gosh, I get -2. This could be a really confusing example. Boy, I hope I'm making that clear enough. Now we've got some algebra. This might feel a little bit more comfortable to you. Okay, how do we do one like 14? And it says do f of g of 4. So that means I'm going to go f of g of 4. So I'm going to take 4. I'm going to plug it into my g function. There's 4 right there getting plugged into the g function. So that means I've got f of 2 times 4 squared minus 1. Okay, I'll write that down. That's 16 times 2 is 32, minus 1 is 31. So now I've got f of 31. Boy, I hope it's not going to ask me to do too much with 31. I plug 31 in for x in the f function, and I get 3 times 31 plus 2. I get 93 plus 2 is 95, I think. I hope I'm making that clear, what to do there. Hey, please try the first bunch of homework problems that I've got assigned for you where the numbers are like I just did in those examples. And then we'll try some of these straight up algebra problems that you start seeing on number 23. Okay, good luck. Hope that makes sense.